Thank you all very much. I'm really excited to be here. Rob, am I supposed to have something on for the camera? No, we're good? Okay. So we're going to talk about structure. And the reason is because I taught second grade for 14 years. And any second grade teachers here? It is the best grade, right? Just be honest. So here's the thing with structure. The last 3 years that I taught second grade, I was part of a research project that explored building algebraic reasoning in kindergarten through grade 8 to help students really develop their computational fluency, procedural fluency, and it changed my whole perception of how kids learn to build that kind of reasoning. And my students excelled with their facts, with their just computation in general. It blew my mind. And so we're going to dig into that today. You're probably wondering why we have the matrix up. Well, because the way my brain works is I always see metaphors and analogies and parallels. And The Matrix is one of my favorite movies. And as I was watching The Matrix, I couldn't help but see the parallel with math education. So who has not seen the movie The Matrix? Okay, so I don't want to leave you in the dark right now. So let me give you just the basics of it, the Cliff Notes version, if you will. So The Matrix is a science fiction film that takes place in the future. And the protagonist is Neo, played by Keanu Reeves. And he's just a regular dude. He works in a cubicle. He's a programmer. He has a regular, boring life. Except one day, he gets a phone call from Morpheus, played by Lawrence Fishburne. And Morpheus tells him that the world he is in is not real, that humans have been taken over by machines and are plugged into a simulation that makes it feel like this world that we're all in, but it's not. Humans are actually all in these pods and are providing electricity for the machines. And so we're basically just batteries. And he learns that there are freed humans that are not plugged into that system, and they're the resistance that are going around trying to unplug all of humanity and save humanity. So, of course, they asked Neo, would he like to be unplugged? And, of course, to keep the plot going, he does. And he meets people like Cypher, who's one of the resistance fighters. And he learns that when you're outside the Matrix, the world looks very different than what it looked like when you're in the world, and that you can get plugged back in. But when you get plugged back in, there are programs that look like humans called agents whose sole purpose is to stop people from being unplugged. And they will kill anyone who goes into the Matrix to do that. So Neo has to undergo some really big training. Part of the training is just self-defense. He has to learn combat training and how to protect himself, especially against an agent. But the bigger part of his training that Morpheus would tell him is he said, I need to free your mind. You can't see this world when you're plugged into it as a real world. It's a computer world that's governed by rules. And if you understand those rules, they can be bent and broken. And so instead of seeing the world like this, he wants Neo to free his mind and to see the underlying structure that makes that world up. And once he can do that, once his mind is free, he can start doing things like jumping across buildings or running up walls or flying or stopping bullets, all of those things. And that's where this movie gets really exciting. And this is where the connection to math comes in. So why am I talking about this? Because I'm going to make an argument that we all grew up in what I call the matrix of math. In the movie, the matrix is a system governed by rules. The math I was taught was a system governed by rules. There was one way to add, there was one way to subtract, one way to multiply, one way to divide, and we just followed the rules. And if you look around today, you'll see many adults that are trapped in that matrix. If you're ever in this grocery store and someone's doing an error algorithm, right? That's someone trapped in the matrix, right? Or one time I travel a lot and I was at a hotel years ago, and I needed to buy one postage stamp. I went to the desk at the hotel. I said, do you sell stamps here? They said, we do. And I said, I need one. And he said, great, he got it. I gave him $1. And then he looked at the dollar. And then he got a notebook out, and he wrote 1.00 minus 38 or whatever the cents was and for the stamp, and did the algorithm to calculate the change to give me back. That's the matrix. I used to tutor a lot when I was teaching in second grade because you don't make a lot of money, so you got to pick up money wherever you can get it. And I was working with these kids in grade 3, and their teachers told me that there's just a lot of stuff. They get really frustrated really easily. And I gave this group this problem. It was 200 minus 198. And I gave it as just a quick warm-up. Like, let's just start with this and do it in your head. And some kids were able to do it pretty quickly. One kid was so frustrated, he started to cry. And I asked him, I said, what's going on? And this is what he said. I can do it if you let me use my notebook and pencil, but I can't keep track of all that borrowing in my head. Turn and talk with a partner. How does this kid see subtraction? Turn and talk. How does this student see subtraction? What's going on? What's their interpretation of subtraction? Procedure. It's just a thing, there's just steps you perform. That's exactly how he saw it. He was taught, whenever you see that, you put the big number above the smaller number, and then you do a line and you go through all those steps. Now, here's the thing. That's what trapped in the matrix is. And you can start to unplug kids. So what I said to him, I said, forget about that. I said, just, what do you know about those numbers? And he said, well, they're kind of big. I said, what else do you know? He said, they're close to each other. I said, how close? And he said, 2. And then he's like, oh, 2. It dawned on him. Because all we had to do is pull him away from this rule for a moment. Now, it didn't mean like right after that, he was completely free. Rule-driven math is hard to break. But you can break it by helping kids step outside the procedure and just make sense of what they understand and use that to begin to make sense of addition, subtraction, any of these. Now, I want us to compare this student's thinking with Keisha. Keisha was a second grader. I told you I was part of this research project, so my colleague across the hall, who was my mentor, was also part of it. Keisha was in her class, and I was in that class observing when I saw this happen. The class was given this problem to do mentally, and at first. And so then they were asked to estimate it mentally. Keisha calculated it mentally, and then they could use paper and pencil, etc. I'd like you all to do this right now. Solve this problem in your head. Then turn and discuss with the person next to you what your answer is and what your strategy was. Could someone share your strategy? Well, actually, let's first, before we do that, let's get the safety thing. What's the answer? 48. Okay, so now if you're like, okay, 48, I feel I can now share it. What was your way of thinking about it? Would someone share their strategy, please? Sure, go ahead.
85 minus 35 is 50.
And before we do this, so what did you do to 37 to make it 35?
I took 2 away.
All right, so I'm just going to show that right here. So you did then 85 minus 35 equals what?
50.
50.
And then subtracted 2 more.
And why did you subtract 2 more? How did you know to subtract 2 more?
I only subtracted 35, and you're supposed to subtract 37. So
Oh.
subtract 2 more.
So you didn't take all the amount that you needed to take away from that. So you had to continue a little bit more to get to 48. So here's one quick thing, a nice tip if you do this. With subtraction, because when you change things, you're changing the context in some ways. Context can help us make sense of what's going on. Can someone give me a context for 85 minus 37? What's the context for that?
What's the distance between the 2 numbers on the number line?
Okay, so we could ask the question, yeah, what's the distance if we have 2 numbers on the number line? What's the distance? So we can look at a distance model. We're going to actually come to that in just a second. Can someone give me a context with removal first? I had $85 and I spent $37 on my what?
Bracelet.
On bracelet, perfect. So if the story is I have $85 and I spent $37 on a bracelet, what is your name?
Abby.
Abby changed the story. How did she change the story when she made it 85 minus 35? Yeah, she's not given the full 37. She's not paying the full amount, right? She only gave 35. So in order to get the bracelet, she needs to give that extra $2. And so it's a way to help us make sense of that. Now the distance model, comparing these can also help us. If we're saying that 85 and 37, and we're trying to figure out what's the distance between these 2 numbers on a number line, if Abby changes it to 85 minus 35, what has she done to the distance? She actually made it bigger. By how much? By 2. So she made this bigger by 2. And so in order to get the correct distance after she does that initial calculation, what does she have to do? She has to shrink that distance. And so these are just ways to visually or contextually help students understand what's happening. So we're not going to go through all the different strategies that you came up with. I'd like us to actually just look at Keisha's strategy. Now, Keisha did it in her head first. That's what she did. I asked her to write down what she did. How many of you used Keisha's strategy? A few people did here. So this is what Keisha said when I asked her, like, tell me what you did. She said to me, I changed the problem to make it easier. What she meant by that was she wanted the number, the subtrahend, the number she's taken away. She wanted it to be a multiple of 10. So she said, I changed it to make it easier. I knew you needed to add 3 to 37 to make 40. And I knew if I did the same thing to 85, it would give me a new problem with the same answer. So I added 3 to 85 and got 88. Now it's 88 minus 40, which equals 48. She's in second grade, and to me, that's the mathematical equivalent of jumping across skyscrapers. That's what Keisha's doing. Compared to that other third grader who said, I can't keep track of all the borrowing. So notice the difference with these students. Keisha has a deep understanding of the way subtraction behaves. She understands the underlying structure of subtraction, and she's using that structure to make computation easier. If 85 minus 37 is not a fun problem for her to think about, she breaks it and makes it something that she can think about really easily. And she's super confident. Now, sometimes people will hear me tell this story, and they'll say, well, we all have a Keisha in our class, that one brilliant kid who's just thinking way ahead of where everyone else is. Keisha's brilliant. Like, she's in college now. She's going to change the world. I know she will. And her classmates were doing the same thing. This was the beauty of this project that we were part of. And I'm going to share with you how you get students to think this way. And we'll get to it. But I want us to back up and kind of get a nice, easy entry point to see where does this begin and how do we get to this point where second graders or kindergartners or fifth graders can think this way. But it all comes down to this practice standard. Look for and make use of structure. So it says in our standards, this is Math Practice 7, that mathematically proficient students will look for and make use of structure. Now, what does that actually mean when we think about like structure? They're talking about the mathematical structure. Everything in math has structure beneath it. So in younger grades, what this could look like, it's as little as a kindergartner noticing that if you add 1 to any number, the answer is always the next counting number. They can use that. My daughter's in first grade right now. And I remember when she discovered that every plus 1 is just the next number you count. And then and you can ask, like, does that always work? And then they can explore that. And then if that's true, then what about minus 1s? And they can start looking at the structure. Oh, well, minus 1's every number before the number, like as you're counting. And then if you get in older grades, it might be looking at like the distributive property and the area models and understanding that underlying structure to understand how multiplication works. But here's the challenge we have. The matrix of math, just like the agents in that movie, it really holds firm. When you start to break away a little bit, you get pulled back in. And so a thing that happens to us in education is that we've been part of this matrix for so long that as we try to break out of it, things squeeze us in. Testing, pacing, administrators that may be deep in the matrix of math, caregivers, politicians, policymakers. There are people who have influence who may be pulling us in. Now, one of the ones that's often a big one for us is the whole idea of just making sure kids get to where they need to get to. And so sometimes, in an effort to get kids to be faster in math, we gloss over the structure. Now, I'll give you a perfect example of this. Does anyone recognize what this tool is? What is it? It's a multiplication chart, right? We can use this for multiplication. If you've never used it before, so I've seen it a lot. It often, kids will, like, if you're going to do like 7 times 8, you put your finger on 7 and 8, you bring them together, and wherever they touch, there is the answer. And so this is used as a tool to help kids multiply. The problem is there is so much rich, beautiful structure underneath that's hidden. And this just becomes a crutch in a way for kids just to multiply quickly. So I'll see teachers give really cool problems to kids and then pass out the multiplication chart, and kids are just matching their fingers. But they're not thinking multiplicatively. They're not thinking about the structure. Now, with one subtle change, we could take this tool and elevate it. And someone did this. So I want you to look at this version right here. This is called the True Scale Multiplication Grid. It says available at thechalkface.net. I'm going to give it to you at the end of this session. I'll have a QR code with the slides, and you can get that, and there'll be a link to get these resources in here. But what is different about this compared to the other one? Turn and talk for just 1 minute. What do you notice about this? So I heard people saying every one of those boxes is an array. You have a 7 by 8 array or a 9 by 9 array. They're all an array. And so this operates the same way. The true scale multiplication grid, you could still do the finger matching on it. But the difference is the second one reveals the structure. The second one helps students to understand how things are getting bigger, the magnitude of these multiplications versus just a quick tool to get an answer. And so one argument I'm going to make is that one part of this work with structure is that we slow down a little bit to go faster later on. That's the key. And so there's other ways that we gloss over this. So this is one. This is just in the use of a tool. The other can be in the way we do instruction. So as kids are learning to multiply, again, the matrix of math would say, here's the procedure you just teach. And you'll hear people say, why don't you just go the old way? Like, it worked for me. And you'll hear these arguments and things. There is so much rich, beautiful mathematics that's hidden by this algorithm. I'm not anti-algorithm. Algorithms we need them. And we also want students to understand them. And so when we just do procedural teaching, you end up glossing over the structure. So instead, we imagine like a structural approach to this would be for kids to solve multiplication in ways that make sense to them. So it might be with arrays in the beginning, and then they get to area models, and then they learn they can decompose these areas into slightly different ways. And so you can break there's your 10 and your 6 for your 16, and then you can cut this way and make it 20 and 2. And now you've got all these partial products that you can then work through. All of this is, you can see the structure, kids can make sense of it. And then usually from this point, we then say, okay, now let me show you a quick strategy. But what I like to do is think about what are the bridges? So before we go to a standard algorithm, what are other ways that kids could think about it? And so then you could do something like the partial product algorithm. So instead of just doing 2 and carry the 1 and all of that stuff, is you have the students write down the product each time. So 2 times 6 is 12, and then 2 times 10 is 20, and then 20 times 6 is 120, and 20 times 10 is 200. But notice, every single step is also connected to the visual. And so students are able to connect the numerical and the visual really easily and see how it all works. So that way, as they get into more fluent ways, as they start to use algorithms and other procedures, it's built on understanding. And so one thing you can see now is once you have that with the partial products one, where do we see the 32? So if we look at the standard algorithm, where does the 32 show up in the area model? Yeah, the 2 on the right-hand side. And where does the 320 show up? On the left-hand side. And so the structure is still there. It's just hidden. So here's the thing about structure. Math Practice 7 works in conjunction with Math Practice 8. These two go together. Math Practice 8 is students will look for and express regularity in repeated reasoning. That's a mouthful. What that means basically is that a student is going to look for things that keep happening over and over again. And when they see it, they're going to say it. And that's the expressing. So if a kid in kindergarten said, hey, when you add 1 to a number, it's the next counting number, that student is expressing regularity. And then a teacher could ask, does it always work? And they try it through a lot of repeated reasoning, and they notice that seems to happen all the time. That's what Math Practice 8 is. And if you see regularity, that is an indication that there's structure there worth exploring. So what we can do is when you think of these as interchangeable, one doesn't have to proceed. You don't have to notice regularity first to explore structure. You can start with structure and then find the regularity as you do that. Now I'm going to give you 3 things today that you can take back into your work to help build out this work with structure in your classrooms. The first is going to be a light lift. We're going to look at 2 quick questions that you could ask. These are generic questions you could use in almost any instance to get kids working on MP7 or MP8. Then we'll look at focusing a lesson specifically on structure. And then we'll look at some instructional routines that you could try that would also build kids' practice with this. So let's start with the quick questions. These you want to have in your back pocket all the time. If you want a student to work, or your students to focus on regularity, if they say anything to this around, it's a pattern. I see a pattern, or it keeps happening, anything like this, ask this question. Will that always happen? If you ask that question, you're going to go into MP8. Because will it always happen means they're going to have to test it a bunch of times. Let me try it with some bigger numbers. Let me try it with some smaller numbers. Let me try it with odd numbers, with even numbers, with fractions, with decimals. Let's see what happens. Will it always happen? There's repeated reasoning. They start to see regularity. If you want them to focus on structure, ask, why does that always happen? The why means they have to get into there. So why is it that when you add 1, it's always the next counting number? They might start looking at the number line. They might start looking at cubes and seeing that if you have 3 cubes and you add 1, that it's a 4th, and then if you add another 1, it's 5, and that it matches what's on the number line, and they start to see the structure. And this works for anything. It works in middle school math. It doesn't matter. Will it always happen, and why does it always happen are 2 of the best questions you can ask. And you don't have to have a whole lesson plan around it. It can come up organically as your kids are playing with the math. So that's the light lift. If you want to go the other end of it, which is a heavy lift, this is where you're going to make the focal point of a lesson on the structure. Now, the way you can do this with the day-to-day stuff, where I'm not asking you to bring in new things for you to do, is look in your curricular resources. In the beginning, with all the standards and anything that's referencing standards, if you see MP7 or SMP7, that means that the authors of that lesson have identified that there's some structural work worth digging into here. Our jobs as teachers, if you want to make these practices really stand out, you as the teacher have to elevate it. So you can make the decision, we're really going to focus on the structure today. So we're going to do that right now. We're going to do a focus lesson for you as adult learners. So I don't want you to pretend to be a 3rd grader or a 5th grader. I want you to bring your full adult self, all your sophistication, all your math knowledge to this. And when we do this as learners, I guarantee you're going to walk away here with an understanding of our number system that you didn't have before. This is the power of structure work. Now to start, so you're familiar with base 10 blocks. And we know that little kind of the yellow one there, that's our little unit cube. Just quickly, this is going to be like those blink estimates. I want you to think about how much space would 1,000,000 of them take up. Turn and tell your partner right now. Don't overthink it right now. Estimate really quickly. I'm giving you 20 seconds to do this. How much space would 1,000,000 of those cubes take up? One big rule is you want your students' mental energy preserved to think about structure, which means that the computation work has to be brought way down. That means work with small numbers. If I want the kids to understand the structure of multiplication, we're not working with 4-digit by 3-digit multiplication. We don't want our mental energy on computation because we're trying to understand the behavior of multiplication. Think of it as like the way scientists study the behavior of animals in the wild. That's how we want our students to study the operations. They have characteristics. They have behaviors worth noticing and exploring. So the first thing you'll notice is that we're going to work with fairly easy computation. The second thing you're going to notice with structure work is at first it seems basic. It seems really easy, almost to the point of why are we doing this? This is so obvious. If it's so obvious in the beginning, you're doing it right. You need an entry point because I guarantee what will happen with structure work is it's going to ramp up like this. What we're going to do right now, I've done with a blended class of pre-service teachers, in-service teachers, and math professors when I taught at Mount Holyoke College. And an interesting thing happened is that one of the math professors kind of flipped his mind a little bit where he got frustrated with this activity. He said, this is dumb. You need the 4th and 5th dimension for this. And I'd never heard, I'm really? I've never heard that. And he's going into hypercubes and all these things. And this is one of the best moments. One of the pre-service teachers in the early childhood program, she wanted to be a preschool teacher. She just turned to him and she made this quick statement where the math became so obvious with the structure because she was thinking of it visually versus getting into all the abstract areas. So the math here is going to get a little interesting. You're going to have to play a bit. But we're going to start with a nice, easy on-ramp. So here's the first thing I want you to do. I want you to consider base 10 blocks. And if you have a notebook and pencil and stuff, we're going to make base 10 representations. So how could you represent 23 times 1 equals 23? Create a representation of that with base 10 model. With a base 10 model. Like, did you use 2 10s and 3 1s, but organized the long way? So you could have it either the 10s and 1s are separate, or you can make it 23 going across, like 2 10s and then 3 1s horizontally. Did anyone do it differently?
I just circled it to represent the one.
You just circled to represent the one group. Did anyone do it with just 1s? Yeah, we could. How many 1s did you have? Right. So another way we could do that is we could show 23 1s. So we could have one group of 23. We could have 23 groups of 1. It's the same thing. Now, here's the thing with structure. The answer to this is 23. Let's look at the first representation. Where do we see the 2 and where do we see the 3 in that representation? 2 10s and 3 1s. Can we see the 2 and 3 in the second representation? Is it there? It is. What do we have to do? We've got to group it. So it's still there, but we need to group it here. So here's the thing. For this exploration, I'd like us to use the first kind of representation. I want you to create the representation using the fewest number of base 10 blocks each time. And so now do one for 23 times 10. What would that look like? So go ahead, sketch your representation for 23 times 10 using the fewest number of blocks. 200s and 3 10s. Okay, so the answer is 230. Where's the 2? In the hundreds. Where's the 3? The 3 10s. Where's the 0? The absence of 1s. Okay, now I'm going to send you on your own in a minute. But what do you notice about when you look at both representations? What's the same? There's always 2 and there's always 3. There's 2 of something and 3 of something. So for this exploration, I'm going to set you on your own. My only ask is that every representation you make, I want you to always have 2 of something and 3 of something. So you're going to build a representation for 23 times 100, 23 times 1,000, and if you have time, 23 times 10,000. Always having 2 of something and 3 of something. Go ahead. You can see what I mean, where the math professor kind of like flipped his mind a little bit, where he's like, we need hypercubes, because in the beginning it's like, dude, we already know this. This is really basic stuff. But as you dig in a little further, like I think the next one, people still felt okay, right? How do we represent 23 times 100? 2,000s cubes and the 300 flats, right? So we're still fine. So why did all the wheels fall off when we went to the next one? What was the problem? What happened?
We haven't seen the concrete model.
Yeah, they don't make any base 10 blocks bigger than the 1,000, right? That's the end, right? There's nothing after that. So that's where you need the fourth dimension. No, you don't need the fourth dimension. That's where you can see, you appreciate early childhood teachers who just have a very visual sense of the math, and that shows the power of visual representations. So we needed to create our 10,000 blocks. Now, there's some interesting ways that people go about doing this. And so the first I'm going to ask is, as I visit around, did anyone solve this problem by just renaming the value of the blocks? Yeah, you could do that. So what could the little yellow cube become instead of 1? It could become 10. So one way we can handle this is let's just make the 1 now be 10. And if a cube, that little unit cube's a 10, then what's the rod? 100. And what's the flat? And then the big cube is? So we could sketch that model right now. So we could say, so this now becomes our 10,000. And this is our other 10,000. So there's our 20,000. And then we have 3 flats. So that works. But what's the problem with it when we look up at here? the visual stops, right? And now it's just like, all right, second verse, same as the first. Let's just keep doing that, right? I'll just copy and paste that thing to infinity, right? We could just keep going because all we're doing is then the next one we make the little cube now 100. And so we can do that. It's great for kids to do that, but you lose sense of the pattern, the regularity. So then there were some other creative ideas. Did anyone here decide to just use almost like a surrogate object to represent 10,000? So I've seen this before where people are like, okay, our 2 phones are 10,000, and then we have the 1,000 cubes for that. And that can work too as a substitute, but again, you lose the structure. So then the idea is, well, can you use the existing base 10 blocks to create your 10,000s? And so that's sort of where people's heads eventually go. And then it becomes, well, what shape will it be? And I've heard people tell me it's going to be a cube, it could be a pyramid, it can be a lot of different things that can come up. And I'm going to actually come over to Naomi. Naomi, you had an interesting way to think about it. So what was your structure? Tell us a little bit about your thinking of how you came up with that, like the design you have for 10,000. And so you could either, if we had the blocks, you can build a 10,000 tower, right? But notice, what was the first thing Naomi said? In order to maintain the pattern. So we see regularity and structure playing together here. In order to maintain the pattern, she wanted to keep that same pattern. So let's talk about the pattern now. So what is the very smallest base 10 block? What shape is it? It's a cube. It's this little teeny tiny cube. If you make it 10 times bigger, what shape does it become? It becomes a rod. If you make that 10 times bigger, what shape does it become? It becomes a flat. If you make that 10 times bigger, what does it become? It becomes a cube. And if you make that 10 times bigger, what does it become? And if you make that 10 times bigger, what does it become? A flat. How much is that flat worth? 100,000. You want to keep going? If you make that 10 times bigger, what does it become? It becomes a cube. And how much is that cube worth? 1 million. Yeah. Hey, you thought it. I just knew to say, you can't say 1 million and not do the Dr. Evil, right? It's 1 million. Now, just let's think of my first question, which was, if you have a little unit cube, if we had 1 million of them, how much space would it take up? I want you to think of your estimate. And now I want you to think about this structure of base 10 blocks, of things getting 10 times bigger, 10 times bigger. Talk at your tables. How much space would 1 million cube take up in this room? Go ahead, turn and talk. About the same, right? It's about right? It's all the uniform dimensions, right? So if you think of that 1,000 block and 10 of them high, and 10 of them long, and 10 of them deep, it would just fit right on your table, basically. So how many of you had an estimate that was way bigger than that? Yeah, which is fine. That's okay, right? We were never given the opportunity to explore the number system in such a way. Now I'm going to ask this question about that cube, rod, flat thing is, does that pattern continue forever? Will it always happen? Yeah, right? So if you think about it, we had our 1 was a cube, and then our 1,000 was a cube, then our 1,000,000 was a cube. What's the next cube after the 1,000,000? What's the next cube after 1,000,000? 1 billion. What's the next cube after 1 billion? 1 trillion, right? And so we see this pattern happen. You're already saying this is always going to happen. Now, to quote the Matrix, if you really want to bake your noodle, what happens on the other side of the decimal point? Will that pattern continue? Now, to do this, here's the hard part. When you want to think about like fractional amounts here, is that unit cube, if we're going to cut it up, it's hard to see. So I'm going to use another movie reference. We'll get a little Honey, I Shrunk the Kids action here. And let's enlarge that for us a little bit so we can actually see it. So there's our little unit cube. That's still worth just 1. My question is, if I cut that into 10 equal pieces for my 10th, what shape will the 10th be? It'll actually be a flat. Okay? Now, if I cut that, so there's our 10th, it's a flat. If I cut the flat into 10 equal pieces, what shape will I have? I'll have a rod. That's our 100th. And if I cut that into 10 equal pieces, what will our 1,000th be? It'll be a cube. And so does the pattern continue. Yeah. Now here is the thing. How many of you, by show of hands, learned something new about our number system today? Yeah. This is the thing that I think is mind-blowing around structure work. When we do this work, we start to understand the underlying structure of our number system, or of operations, or of decimals. And the thing that's powerful with this is it doesn't matter what age you are. Structure work is eye-opening. It is really eye-opening. And one of the best things that you could do for your students to help them explore structure is to explore the structure yourself, to play around with how else can you visualize the math that you teach. And that is helping to make the structure visible for you, which you can then replicate those kinds of experiences. Now, the thing that's really important is a lot of times when I do this with teachers, they'll be really excited and they'll say, I can't wait to show this to my kids. And I'm always like, no, don't show them. I can't wait to have my kids experience this thing. Let them discover it. Because if I just showed you it, it's not nearly as powerful as when you discover it. You mucking around thinking, maybe this will be a big cube, or no, I don't think I can make a cube with this, and maybe I could. All of that is where you make sense of the structure for yourself. Being shown the structure is, in a lot of ways, is also kind of procedural in a way. It's like, you just know it because, trust me, bro, versus you know it because I've explored it and I've come to understand it. And so now the last one we're going to play with, so that's like a deep dive if we want to get into that visual piece, is let's look at an instructional routine. And this is what Keisha's class did. We're going to go back to Keisha and my class. And so to remind you of Keisha, she's the one that was jumping across buildings in math along with her students. So how do we get here? So this is the thing that I'm excited to really have you think about bringing into your spaces. We had this algebraic reasoning routine that we did as part of the research project. And I'm going to tell you a little bit about the project and what was asked of us. The researchers, who were my colleagues, Susan Jo Russell, Deborah Shifter, and Virginia Bastable, they did not want us having to upend our math day. They didn't want something that would take an exorbitant amount of time. So they made us commit to doing this for 5 minutes a day. That's it. 5 minutes. Can you carve out 5 minutes? Even, like I did during morning meeting. I didn't even do it during my math block. And sometimes we weren't allowed to go any more than 10, but we really tried to keep it to 5. They did not want us saying our whole math lesson today is going to be this, because you all know as teachers, the last thing you need is one more thing. Right? The last thing we need is one more thing to do. And so they wanted something that could be complementary to what we're doing. And the work that we did actually produced these 2 books. You do not need to get the books. They're my colleagues' books. I'm not one of the authors. My classrooms are in there. But it's the work was so powerful that 2 books were produced by it. And I'd like to take you through this routine. And we're going to do it in parallel to like my second graders. And so the very first day, we asked students to notice regularity. And what we did is we just grabbed a piece of student work, a pattern that came up. This was one that we saw. A lot of kids were doing this. And we had an activity in my class called Today's Number. So it was 36 for that day. Make today's number as many ways as you can. And some of my students would sort of hack the system. Like the kid who did this, I could tell, I remember, he didn't even do like 37 minus 1 equals 36. And if I go to 38 minus 2, he wasn't doing that. He went 37, 38, 39, minus, 1, 2, 3, 4, equals. He was not even paying attention to that. So we thought, let's capitalize on that. And let's just, like, what do you notice? So right now, what do you notice? Turn and talk for a minute. What regularity do you see there? What patterns do you see? Go ahead and just talk for 1 minute. My kids were saying the first number goes up by 1 and the second number goes up by 1. It's all minus. They all have equal signs. All the things that kids would say. Some kids, like the thing they notice is it's a pattern, right? That's another thing little kids will notice. Like, well, yeah, it is, of course. Like what? But what's the pattern? So that's day 1. That took 5 minutes. I listed everything they said. And then the next day, we asked them to make a general claim. And so we had all their noticings. And the general claim was, like, we didn't call it a general claim. We basically said, what's the rule? So if this is always going to happen, can you state it as a rule? And we would give them like sentence frames, like in subtraction, when or if, and like if-thens and stuff like that to help them play around with it. And they had to state it in a general way. I'd like you to do the same thing. So if we say that this will always happen, that as these numbers, if we went to 41 and 42 and stuff, if that's going to keep going forever, what's the rule? In subtraction, when we do this, then this happens. Turn and talk at your tables. What's a general claim you can make about this? In subtraction, if the first number changes, the other number needs to change by the same amount in order to have the same answer, right? So a little actually expanded beyond what we're seeing here, beyond just the increasing by 1. So you get the idea. It doesn't have to be overly complicated here. This is what my kids came up with. When you add 1 to the first number in a subtraction problem and 1 to the second number, the answer is the same. That's it. That's a great second grade generalization. And but think about just that understanding right here. Yes?
What I love about it is a student may figure that out, but they don't know why.
Yeah.
Right? They understand the structure.
Yeah.
Especially particularly if they're younger, right? Like they probably haven't experienced too much mathematics, but they figured that out.
Yeah.
So I would be so impressed that a kid figured that out in like 2 seconds.
Yeah.
Like that right there. But then to give them the language or to give them the mathematical reasoning, to give them the structure, and then continue to extend that.
Yeah.
Like I think that's where your goal is.
Yeah.
That's where your extension is. When sometimes you're like, all right, you got the right answer, you're good, I'm moving on.
Yeah.
But that's where you can do the enrichment.
Yeah, your fast finishers, this is really good work for your fast finishers. And actually, it's good for everybody, but a lot of times you have your fast finisher, well, let me just give you more numbers to work on. But instead, you could say, why does this work? And can you prove it? So this is a really powerful statement. Now, this day took 5 minutes. It was 5 minutes. They turned and talked, and then we did it. We co-constructed together with different kids adding different pieces. The original one was when you add 1 to both numbers, the answer's the same. And so then I asked questions like, so for any, like, does that work with addition? And they're like, oh, no, hold on. So then we had to put subtraction in. And so we helped them kind of, I wouldn't write it for them, but I would ask questions to poke holes in their general claim. But it was a 5-minute shared writing experience, and that's it. So we're 2 days in, 10 minutes total right now. So the next day was to test the claim. So what we did is I put the claim up on the board and said, you remember yesterday you said this, and I also had their patterns and all their observations. I said, a fun thing to do in math is when people make a claim is if you can disprove it. And we talked about what disprove means and how you find an example where it breaks it and stuff. And their kids are like, I can break this thing. So then they're excited. So to test the claim, they all just start working on different examples. So that they make a subtraction problem, and then they would add 1 to both numbers, and they would see if they could break the rule. And they would try, and every once in a while they say, I did it, I broke it. And then it was actually a calculation error and stuff. And we found that, in fact, the claim holds true. Now at this moment, this is day 3, again, we're about 15 minutes of work in, and this, for a second grader, is enough. If I just tried it a bunch of times, it's like, yeah, it totally works forever. Mathematically, though, like in the math world, that's not enough. Proving by examples is not enough to really justify a claim like this. So what we actually need to do is create a representation-based argument. So the reason I call it a representation-based argument is because it's inclusive. Because representations can be manipulatives. It can be a visual representation. It could be a numerical representation. You could express it algebraically. The kids are not going to do that, but all of those are forms of representations. So the rule we had, this is where it got a little harder. This took more than 1 day because we wanted to stay with that 5 minutes, is the criteria was, and this is written for adults, the representation has to show the operation. So what I told my kids is, however you show it, I need to see subtraction. The other criteria was that the representation has to show that your statement, your claim, works for all numbers. And in the case of second grade, it's all their counting numbers, right? That's basically their whole numbers. And you get in older grades, it's like you can just decide the domain. Are you talking about rational numbers? Are you just talking about integers? Like what's the domain you're going to work with? But for this, it's just the numbers the kids know. And so basically, I have to show that you have to show it works for all numbers. And the last one is that the conclusion of the claim, like your argument, needs to be seen in the representation. So I'd like you to think right now. The claim that when you add 1 to one number and 1 to the other number in a subtraction problem, the answer stays the same. How would you prove that using a representation that shows subtraction and fits this criteria? So I'd like you right now, we're just going to take a couple minutes. At your tables, what's a representation that you could make to prove that that claim works, that shows that it works for all numbers and that we can see it. So you could either sketch it like with cubes, you could sketch it with number lines, whatever you want to do. But give it a shot, and then I'll show you what the second graders did. You all have really good representations, and the hard part is how do you show it works for all of numbers, right? A lot of the representations have like specific numbers on the number line, and so that was the harder part. I'll be honest, like when kids can get to that spot, it's really exciting. They don't need to have, like I'm satisfied if they can show that the structure is evident there. Because of the project, we pushed on it a bit. It's worth it over time, but the first few times you do this with kids, you don't need to stress that it's got to work for every number. For adults, yeah, I'm going to you got to do it. Like, I'm going to make you work, but let me show you what the kids did. So here, they had them work in groups of 3. So this is a group that showed their representation on our smartboard. And so I'll just say originally when they came up here, they had all 3 of those things had specific numbers on it. And the actual class, not me, said, hey, that doesn't show it works for all numbers. So they wrote any number basically. But here's how they did it, is they said the space between any numbers on a number line is the answer. And if you add 1, they showed that next bar, they said it's basically the same thing. And because it was a smartboard, that next bar they drew, they could drag it back and forth and said it's the same distance when you add 1 to both sides. So I want you to think right now is, where do we see subtraction in the representation? So where is subtraction evident? The actual distance, right? They're using a distance model of subtraction. How does it prove the claim? It's showing the shift with the same distance. And how are they showing that a claim works for all numbers? Any number, right? Which is great, right? That's a helpful thing. Any number. So that's a number line. You can just label it with any numbers or blanks or shapes or whatever you want to show it works for any numbers. Now, this next one I had to recreate because I didn't record it. But the kids came to the floor with 2 stacks of cubes. And what they said here, they're using a comparison model. The subtraction here is red compared to blue, and the difference is green. That's their comparison. So this is what they did, and it blew my mind. They took the difference off, and they added 1 yellow to each one, and put the same difference back in. Right? This was, now these are 7 and 8-year-olds thinking about subtraction this way. Most second graders up until that point, in my class it was included, is that subtraction is always thought of as just takeaway. And these other models of subtraction are not as well understood or as well experienced by kids. And they're using it to prove this claim. Now, there was an argument made. One of my class members said, well, you can just count all the cubes, so that just shows it works for those. How do you show it works for any number? And one of the kids covered up the bottom with his hand, and then we got some paper. And we said, if you don't know what's underneath that could go on forever. And so that shows it works for any number. Now, I want you to compare these kids to this 3rd grader saying, I can't keep track of all that borrowing in my head. This is what unplugged from the matrix looks like. They are not bound by the rules. They understand the structure of subtraction. And we're not done. Like this took us 3 days to get to this point. 3 days, I'll be honest, like we kind of got near the 10 minutes each day for the representations because it was harder. I did have an observer in the room, so I couldn't go past 10 as much as I wanted to, but we just stretched it out over 3 days. But once we got to that spot, then the next part of the routine was to revise or extend the claim. These things actually were coming up as we were exploring, but the 2 things my class came up with is if you add or subtract 1 from both numbers, the answer stays the same. And then some kids thought if you add or subtract any amount, kind of going back to what you said, and then you do the same thing to the other number, the answer stays the same. And what's great is when you revise or extend the claim, they don't have to start back and test it and all of that. They can take their representation-based argument and try it again. So we could take this, take the difference off, and add 4 to both, and see that it still works. And so now you get to the spot where they understand structurally how subtraction behaves when you maintain the same difference. And so then we want to apply it. So, because the big thing is like, now you know this, well then how can you use this structure to help you? And so I would give them a problem and say, can you try this rule? Can you try this? And so it doesn't mean that that's the most efficient way to solve the problem, but they start to realize that you can make any subtraction problem with the subtrahend, the end in zeros, by adding to get to that nearest 100 or 10 or whatever it is, and then do the same thing to the other number, and it'll always work. So when we think of Keisha's amazing mental math, you realize we know how she got there. That's the power of this work. And it's not just for little kids. We did this all across the grades. So I worked with some fourth graders on multiplication, again, thinking things that are obvious. But if you look here, the regularity that we're seeing, 9 times 4 is 36, 10 times 4 is 40, 9 times 7 is 63, 10 times 7 is 70. So they started to notice things. And this is what the fourth graders that I was working with this came up with. When you want to times something by 9, just times the something by 10 and then minus the something. I couldn't have said it better myself, right? And then we do the same thing. Let's test the claim a bunch of different ways. Let's represent it. So here's one where we see the 9 times 5, and then here it's now 10 times 5, and then you just take away that amount there. But the argument that showed it worked for all numbers was this one that a group came up with. And it was, there's your 9 times something, there's 10 times something, and then you just minus that something to figure out what your 9 times something is. This is the power of this kind of work. Revising the claims, if you want to multiply something by 11, just multiply the something by 10 and then add the something. If you want to multiply by something by 12, just multiply by 10 and then add 2 somethings. Like, there's some powerful reasoning that comes in, and then students can start to apply this to problem-solving situations. So if you look at the definition of computational fluency, it'll say that kids can solve problems efficiently, accurately, and flexibly. This is how you build flexibility. You understand structure. When you understand structure, then you bend and break the rules. That's how you become flexible. Now, in order for any of this to happen, if you're going to unplug your kids from the matrix, you yourself have to be unplugged. You have to buy into this. You have to understand that it's not about that algorithm, that the algorithm is a way to do it. It's not the only way to do it. And so I'd like for you, I'm imagining you're all here at a conference like this, that none of you are plugged into the matrix anymore. I believe that you're all out of the matrix. So I'd like you to reflect for a moment about who was the person that unplugged you. Because we've all had somebody or a group of somebodies that gave us an experience. It could be a math coach, it could be a colleague, it could be a professional learning experience you had, it could be a book you read, it could be a teacher you had or a professor you had. But all of us have somebody that opened our eyes to recognize that the math world that we thought we knew doesn't exist. It's a very tightly narrow control world that we can now open up when we're outside of that. And I'll just tell you about my Morpheus. So Morpheus is the one that did the unplugging in the movie. I was fortunate because Morpheus taught across the hall from me. So that's my Morpheus. That's Anne-Marie O'Reilly. She was my partner in crime. When I started teaching, I was a terrible math teacher. Let me fix her up a little, make her more like Morpheus. There we go. Now she's Morpheus. Okay. She's the one that unplugged me. And she did it in just like through conversations and through experience. And she encouraged me to get training. And so when I was unplugged, I went and I did the training that Neil, well, not that kind of training. Here's my training. So there's 26-year-old me in my first math PD getting my brain broken. And this was really helpful. Now, here's a couple of just parallels to take with you on this journey, because as you recognize when you're out of the matrix, not everyone in your world is unplugged. And you might get pushback, right? How many of you have had any caregivers or colleagues or somebody say, why are we changing math? Like, raise your hand if you've heard a complaint about new math, right? Do you want to understand why it is? The movie has it. And I'm hoping the volume doesn't, let me just give it a shot here, but I want us to watch a small clip. This is a clip when Morpheus is still teaching Neo about what the matrix is, okay? Let's listen to what he says.
The matrix is a system, Neo. That system is our enemy. When you're inside, you look around, where you see businessmen, teachers, lawyers, carpenters, the very minds of the people you're trying to save. But until we do, these people are still a part of that system, and that makes them our enemy. You have to understand, most of these people are not ready to be unplugged. And many of them are so inert, so hopelessly dependent on the system that they will fight to protect.
So you have to recognize that fear can sometimes drive some behaviors of people in the math world. And if I only know the matrix of math, if I only know one way to multiply, because I was a good student, I followed the rules. And now my kid's coming home with things that don't look anything like I recognize, and I don't know how to help my kid, I'm starting to feel dumb. And that triggers amygdalas. And that means I'm now like going to get defensive, and I want to dismiss things. And so if we understand that that pushback we're getting is not because someone has ulterior motives or that someone wants to undermine and sabotage what we're doing, it's likely that they don't understand what we're doing and they're afraid. And the best thing you can do is work to unplug them by helping to teach them. And so a way you can think about it is I've created a matrix Morpheus continuum. And on the one hand, you've got Morpheus fully unplugged. This would be you. I know that kids need to think about math flexibly in different ways. And on the other end would be like an Agent Smith, which is like actively revolting, like going to school board meetings and fighting against any changes, right? There are Agent Smiths out there. So I want you to think about, where do you put yourself on this continuum right now? And what you'll notice is where you fall depends on the math you're doing. So I feel very much a 10 in K-8 mathematics. The last 4 years I've been teaching high school. I was like a 2. I've worked myself up to about a 7. I'm not a 10 yet with high school because like I don't know how to like make sense of radicals in a way that will help me to teach it in a more Morpheus kind of fashion. So I'm still working on it, but that can change. But I want you now to think about, where would you place some of your colleagues on this? Your administrators, your school board, caregivers of the students in your class, your math coach. And when you start to understand where they are, it helps you to think about reframing how you look at that resistance and that pushback. Because once you are unplugged, you can't get plugged back in. And so you then work to unplug. And you might work to unplug students. What I did is, after I got comfortable with that, I started to unplug teachers. And all of you are in some way, shape, or form are part of this movement to unplug kids out of the matrix. So to end, I'm going to just share with one last quote. So what we're going to see here is a scene where Neo has not gotten unplugged yet. This is his choice moment. And so Morpheus is going to just give him this choice. Let's watch.
This is your last chance. After this, there is no turning back. You take the blue pill. The story ends. You wake up in your bed and believe whatever you want. You take the red pill. You stay in Wonderland. And I show you how deep the rabbit hole goes. Remember, all I'm offering is the truth. Nothing more.
And so while I don't condone drug use, if you're so inclined, take the red pill. Thank you.